Hi, everyone. Thank you for the introduction. I want to graduate in 2 years. So let's begin. So before getting into all these new isolation mechanisms, well, he didn't introduce my paper. So today we'll be looking at limitations and opportunities of modern hardware isolation mechanisms. And before we get started, let's have a flashback to the history of isolation mechanisms. The first computer architecture were batch machines, which executed one program at a time. In 1961, the Burtsev B5000 introduced segmentation. The next year, 1962, paging was introduced by Atlas Computer. Since then, for over 4 decades, a range of user-level and kernel-level projects explored the possibility of providing practical and low-overhead isolation. Here's the list, quite a few of them. So here's a question. Why do we need efficient isolation? Well, a range of modern applications with tight performance budget require fast isolation boundary switching and low runtime overhead. But for a very long time, what we had was segmentation and paging. Unfortunately, segmentation was deprecated, and the page table requires 800+ cycles for domain switch, which is not ideal for modern applications. For example, DPDK spans less than 100 cycles on one network packets. Lucky for us, in recent years, we see a wave of new isolation primitives. Intel memory protection keys, ARM memory tagging extensions, ARM pointing authentication code, and ARM cherry capability model. Specifically, in this work, we'll use ARM Morello board, which is the first silicon implementation of the cherry capability model. So here comes the question we want to answer today. Are we doing it right? Are these primitives finally, the ideal primitive that we all wanted? Almost. So what are we looking for from these new mechanisms? Specifically, we're looking at 4 design principles. We want low overhead of enforcement. Anything with more than 5% overhead is unlikely to be adopted. We want fast switching of isolation boundaries. For applications with frequent domain switching, like high-speed trading or network packet processing, overhead of domain switching greatly affects the performance. And we need zero copy of passing of data. System device drivers, network functions, data centers, and databases, etc., require frequent passing of data between isolated subsystems. In these systems, the overhead of passing data between systems is very prohibitive. Last but not least, we need move semantics and revocation. This might sound not that important, but it's actually very important. This kind of move semantic is critical to prevent a range of time of use, time of check attacks. Internally, the ability to move something is rely on the ability to revoke access right from the caller to the callee. Imagine if the caller cannot make sure that the callee cannot access the buffer anymore. In this case, the callee will simply just copy the buffer again, just to guarantee safety. Surprisingly, in this work, we found that revocation is very challenging. To evaluate each isolation mechanisms, we use a generic isolation scheme. We use the migrating thread model to avoid overhead of a context switch. We maintain a private heap for each subsystems. And we use a shared heap to allocate shared buffers for communication. Here, system A wants to invoke a function in B and pass a buffer. A first allocate a shared buffer on the exchange heap, and then invoke the TCB to transfer the ownership. Then the TCB can invoke the function in B. To understand the performance of the isolated mechanisms, we implement a network function virtualization framework, similar to NetBreaks. In our experiment, we isolate 4 different network functions and test their performance against different batch sizes. Here comes the fun part, my favorite part. How do we implement these isolations using the new primitives. Intel memory protection key allowed users to tag virtual memory pages with one of 16 different keys. A per-core PGL register is used to hold accessible key for that CPU core. Here, a fault will be triggered if a CPU is trying to access a memory region which it doesn't have the key for. We use CET and binary inspection to achieve isolation. Here's how it works. First, each subsystem's private heap is tagged with a different PK. And the shared buffers is tagged with different PKs. The system can invoke a TCB to transfer the ownership of the shared buffers, and also call into different domains. The use of binary inspection and CET will eliminate any write PGL instructions outside of TCB. Our memory detection extension allows the users to tag each 16 byte of memory region with one of 16 different keys. Here, the unused bit in the pointer are compared with the memory tag upon the memory access. Therefore, if we want to access the green region, it will trigger a fault. In our model, each system wants a specific empty tag. Its private heap and shared buffer is all tagged with the same key. When we're trying to move a buffer from one system to another system, it's simply retagged. We use compiler rewrite to forcefully inject the tag on each memory access. Here, x28 is reserved to hold the tag of the current subsystem. We use the bitfill insert instruction to overwrite the tag bits of x10 with the tag of the subsystem. Therefore, this memory load is empty protected. ARM cherry-KB model extends the registers to be 128 bits capability registers. Each capability, in addition to the address, also stores the bounds and permissions. So they can be used to achieve isolation. Capability pointers are supported in all models. However, we use hybrid mode in this work because it also support legacy pointers. When a non-capability pointer is dereferenced, the DDC, default data capability, is used. Here, we'll use the DDC to implement the private heap for each domain. When the domain allocates a shared buffer on the exchange heap, a capability is granted to it. Now, A can pass the capability to B, and B can freely access this shared buffer and store the capability in any registers or on its private heap. Therefore, in Cherry, there's no support for revocation. To support revocation, we use a compiler rewrite to catch all the stored capabilities on the heap. Here, domain A wants to store capability on its private heap. A hash table in the TCB will catch it and record the fact on the hash table. When the domain exits, all the stored capabilities on the heap will be erased according to the hash table. ARM pointer authentication code can cryptographically sign a pointer with a signing context and a secret key. PAC was not directly designed for isolation. However, with compiler instrumentation, signed pointers can work similarly to the Cherry capability pointers. For the sake of time today, I will not go into too much details. I'll give a high-level look. Each object is signed with the size of the object as a power of 2, and the base address and the secret ID. The size bit and the PAC is used to index into this hidden map in the memory to store the secret ID. If the subsystem wants to dereference into this pointer, the size, PAC, and the base address has to be the same. And the secret ID must be present in the table. Therefore, we can revoke any capability just by erasing the secret ID from the table. As a baseline, we also measure the performance of a purely software isolation scheme, similar to Google native client. A 32-bit move instruction is used to clear the upper 32 bits of the address. R15 is reserved to hold the segment, which is the base address of the private heap. This load instruction uses RAX plus R15 as the target address. Hence, this memory access is always within the bound. ARM SFI is similar. It's the ARM version of Google native client. X28 is similarly reserved to hold a segment. A bit fill insert instruction is used to overwrite the up 32 bits of X10 with the segment, and we achieve the same isolation. To understand the pure runtime overhead of each isolation mechanism, we run a collection of spec 2006 and 2017 benchmarks. MPK plus CET has overhead less than 2%. Macro like SFI has average overhead of 17%. Similarly, on ARM, it has 18% overhead. Due to more reserved registers, MT has slightly higher at 20% overhead. PAC has over 100% overtime because of complex compiler rewrite and fetching of secret ID. From the benchmarks, we can clearly see that SFI, MT, and PAC all have prohibitive overhead, all over 15%. To better understand the source of overhead, we'll do a detailed breakdown. Reserving one register and forward return edge checking only have 3 to 0% overhead, whereas the masking instruction in front of every load and store has up to 20% overhead. Similar to ARM, that instruction has up to 36% overhead. This brings up the first principle, software transparency. Isolation mechanism should minimize the use of compiler rewrites because it affects the performance dramatically. Possible solution for MT. Well, for MT, a protected register similar to PKRU can be used to hold a tag and automatically apply it in the hardware for every memory load and store. Instead of a general purpose register, here we use a segmentation register to hold a segment. This move instruction uses the lower 32 bits of RAX and the GS register to calculate the final target address. Hence, we achieve the same isolation as previous slides. This trick can bring down the overhead to just 4%. So for SFI, the use of GS register can eliminate the added instruction. So maybe we can implement a special mode of instructions where the segmentation is forced automatically. Here we look at the overhead of switching isolation boundaries. These 3 lines measure the overhead of an ideal trampoline, in which the isolation boundary switch can be done in just one cycle. SFI, MT, and ARM PAC all have overhead similar to this. Morello switch uses the trampoline to switch into the executive mode to change the DDC to a target calling domain, and then switch to restrict mode to continue execution in the next domain. It has around 100% overhead. MPK comes at worst, with over 250 cycles overhead. In the network function virtualization workload, the ideal hardware assumes that there exists an ideal hardware primitive, like the slide showed before, which can switch the domain boundary in one cycle and has no runtime overhead. We can see that even with the ideal hardware primitive, at smaller byte sizes, the performance is very poor. As we expected, MPK performs extremely bad at smaller byte sizes. However, because it has low runtime overhead, it comes head-to-head to the ideal hardware at higher byte sizes. From the experiment, although far from ideal, we see that SFI, MT, and PAC all have reasonable performance. However, the overhead of Morello and MPK are higher, which make them unsuitable for some workload. Therefore, a good isolation primitive should have low overhead of domain switching. Otherwise, the performance will suffer. To understand the overhead of passing data, we collect the overhead of each mechanism passing data of different sizes. PAC, Cherry, and MPK all have constant overhead of passing data of any size. Cherry takes 140 cycles to pass the capability and revokes one in-memory copy of it. It's not shown in the plot here, but the overhead grows linearly as the number of the copies in memory goes up. To our surprise, MT retagging is only slightly faster than memory copying. Depending on the size of the object, MT is only 1.2 to 2 times faster than memory copying. To better understand the overhead of copying plays in the real application, let's take a look at the performance of SFI on the network functions. For SFI, network packages are copied into different private heaps of each subsystems. As you can see, because of data copying, the performance of narco-like SFI and segmentation trick is very poor. Similarly on ARM, the overhead of copying data affects the performance of SFI dramatically. MT retagging is faster than copying data, but still have a big impact on the performance. As we can see, copying data is simply too slow. Isolation mechanism must support zero copying. Otherwise, we'll see huge performance penalty. Although faster than memory copying, MT still suffer from overhead of retagging. A possible solution could be variable granularity for the tags. Smaller tags will allow for finer granularity of the isolation, whereas larger tag can give us faster retagging time. Similar to MPK, the size configuration of the tag can be stored in the unused bit in the page table entry. To our surprise, although it might sound easy, supporting revocation is very challenging. Capability schemes like Cherry lack support for revocation. Currently, some software solutions are proposed. Cherry Revoke scans the heap of isolated domains to revoke all stored capabilities on the heap. Compiler instrumentations we use in this work tracks all the stored capabilities and revoke them upon domain exit. Can we address this? Well, it's very challenging. We don't have a good solution for it in mind. But maybe some hardware metadata can help us, similar to how we do revocation in PAC. Although there are many software solutions for revocation, Cherry allows the capabilities to be stored in the registers on a different core. Therefore, an expensive inter-processor interrupt is needed to revoke these capabilities in the registers. Similarly, MPK also lacks core-coherent way to update PKL instructions, PKL registers on different cores, making IPI necessary for revocation. Although our PAC schemes support revocation, there's a small window for a time of check, time of use attack after revocation, because the check and the memory access is not done in the same instruction. In conclusion, it's great to see a wave of new isolation primitives. In this work, we identify 4 design principles that we think are critical for an efficient isolation mechanism. As we show in our analysis, no efficient isolation can be built without them. Although some limitations are hard to overcome, most of the primitives can be extended to support all the principles. We hope that our work can be useful in designing the future isolation primitives. And when you are working on a hardware project, keep in mind of these 4 design principles. Thank you very much. I'm here for the questions.